Hello everyone, in this video we are going to discuss about mathematical induction. This is a topic in algebra, or more than that you can say it is a part of the discrete mathematics. Where we usually study the properties of natural numbers or the set of integers. So this mathematical induction basically is a tool. You can say it is a tool to prove complicated mathematical theories that are difficult to prove in the usual sense. So to explain the method or the principle of induction, first of all we need to learn about mathematical statements. So a mathematical statement is usually denoted by Pn, and it is a statement that consists of some mathematical expression the first thing is this: it will consist of some mathematical expression, and the second thing, it will have a definite state. That means the definite state should be either true or it will be false. Okay, so for a mathematical statement we have two things. First of all, it should be it should contain some mathematical expression, and the second thing is that it should have a definite state, a definite state that is either true or false. So usually in the mathematical expression will consist of some natural number n. That's why the notation is this p in bracket n. So let me give some example of a mathematical statement. Example. Suppose we are saying that Pn is a statement that say sum of first n natural numbers is n plus 1 divided by 2. So this can be considered as a mathematical statement because we know that it is true, and it is having some mathematical expression like n plus 1 by 2, and also it is the sum of first n natural numbers. So in this way it will become a mathematical statement. Similarly, we can consider another mathematical statement like this, that say we are taking it like this: 2 into 7 to the power n plus 3 into 5 to the power n minus 5 is divisible by 24. So this statement is saying whenever you are having this kind of expressions where n is n is a natural number, then you can say it is divisible by 24 for every natural number. So these are some simple examples of mathematical statements. Let me give another example, that is the final one. Say we are taking the example like this. It is mod of sin nx is less or equals to n times mod sin x, and it will be true for all x belongs to R. Okay, so these are some mathematical statements, and we will see that every mathematical statement is either true or false, and it is having some mathematical expressions. Here we are having some expression like mod of sin nx less or equals to n mod sin x, and similarly for these two statements as well. Okay, so these are some examples of mathematical statements. So let me now come to the theory or the statement of the principle of mathematical induction. So let me write it here. So mathematical induction says, suppose we are having some mathematical statement Pn, and we are saying that if you put n equals to 1, then P1 becomes true. Instead of 1, it can be any natural number, but it is the first natural number where the statement is being true. Sometimes it is also saying sometimes we also say that the statement Pn is true at some initial point, and here we are taking the initial point to be 1. And this is the first condition here. The second condition is this: if Pm is true, then Pm plus 1 will also be true. So what it is saying, if the statement is true for any natural number m, any arbitrary natural number m, then it will be also true for the immediately next natural number, that is m plus 1 also. So if these two conditions are there, then we can say that the conclusion of the principle will be this: Pn is true for all natural numbers. So let me repeat it again. Suppose we are having some mathematical statement Pn, and we have two conditions. The first one is this: P1 is true, and the second one is, whenever Pm is true, we can say Pm plus 1 is true. So if these two conditions we are having, then we can conclude that the mathematical statement Pn is true for all natural numbers that we know. Okay, so this is the power of the principle, that to verify whether the statement is being true or false over the set of natural numbers, this is enough to show that it is being true at some initial point. Say the initial point is 1, and whenever it is true at some arbitrary point, arbitrary natural number m, it is also true at the immediately next natural number, that is m plus 1. Okay, so this is the statement of the mathematical induction. So let us see how we can use it to prove some mathematical to show that a mathematical statement is valid for all the natural numbers. So let us take the example, the simplest example first. that we consider the Pn to be the first one, that is the sum of first n natural numbers is n plus 1 by 2. Let us consider this one. So in this one we can also write Pn like this. We can write it as 1 plus 2 plus 3 plus dot 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 to n to be n plus 1 by 2. This we can write. So see what we have to do here. First we have to show that P1 is true. Now what is the meaning of P1 here? So the statement says it is the sum of first n natural numbers for Pn. So if you put n equals to 1, it will lead to the sum of first one natural number. That means only 1. So we can say that P1 is nothing but, this is out of the solution. Let me just explain what is P1. So for P1 we can write the sum of first one natural number is 1 into 1 plus 1 by 2. So the first one natural number means it is 1 itself. So we are taking the sum up to 1. That means only 1. And it should be equal to this value. Now see, 1 into 1 plus 1 by 2, that is also being 1. So basically the statement is being true. Okay. So this is the meaning of P1. If you are taking P2, then it will mean it is the sum of first two natural numbers. Instead of 1, now it will be 2. That means you can say it is the sum up to the natural number 2, that is 1 plus 2. And this can be written as, according to the statement, the sum should be 2 into 2 plus 1 by 2. Now you can easily see that if this 2 is being cancelled out, then it is the same thing. So again we are having that P2 is also true. So this is the meaning of the mathematical statement to be true at some point. Okay, so let us show here that P1 is true. So that we will do like this. We will write for n equals to 1, or you can also write as P1 colon. So for n equals to 1, what is the left hand side of the equality? It is the sum of first one natural number. So we can write the LHS to be 1, and the RHS here should be 1 into 1 plus 1 by 2. That means 1 again. So here we can conclude that LHS is equal to RHS. That means the statement P1 is true. So our first condition is satisfied, that is P1 is true. Now we are going to show the second condition. Second condition is also satisfying here. So for that we are assuming that Pm is true, and we will try to show that Pm plus 1 is also true. So using Pm we will show that Pm plus 1 is true. So let us see. So so let us assume that Pm is true. Now since it is true, we are assuming we can write the equality straightforward. That means we can say the sum of first m natural numbers is becoming m plus 1 by 2. So this is we have taken granted because we are considering that Pm is true. So for Pm plus 1, what we will have, or we can say for n equals to m plus 1, what we are having in the left hand side of the statement, we are saying that it is the sum of first m plus 1 natural numbers, that we can write like this: 1 plus 2 plus 3 plus dot 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 up to m plus m plus 1. Why we are writing it like this? We are writing it like this because we have to use the statement Pm when we are proving the statement for for m plus 1. Since we have to use Pm, we should have the expression up to m. That's why we are taking the series up to m in a separate bracket and m plus 1 separately, so that we can now put the value of this 1 plus 2 plus 3 up to m as m plus 1 by 2, and then it is m plus 1. Now if you take common m plus 1, we will get something like this: m by 2 plus 1, and from that you can show it is m plus 1 times m plus 2 divided by 2. So this is the left hand side for the statement Pm plus 1. So let us see what is the right hand side. Usually the right hand side is this one, n plus 1 by 2. So if you are putting n equals to m plus 1, you see we are having m plus 1 times m plus 1 plus 1 divided by 2, because m plus 1 itself is n. So here we can write m plus 1 times m plus 2 divided by 2. So it is the same with the previous LHS, and we can write that LHS is equal to RHS here. That means the statement Pm plus 1 is also becoming true. The last thing we have to write here is the statement that hence, by principle of mathematical induction, Pn is true for all n belongs to the set of natural numbers. So basically, see here, if it is becoming true for n equals to 1, and we are assuming it to be true for any natural number m, and then it is being true for m plus 1 also, then using the second condition, that is it is true for m implies it is true for m plus 1, and the first condition also, that is P1, we can show that it is true for all the natural numbers, because if it is true at 1, the second condition is saying that it is also true at 2. Now if it is true at 2, then the second condition is again saying that it is again true at 3. So in this way, the statement can the statement will hold true for all the natural numbers up to infinity. So this is the application of mathematical induction in this kind of problems. So let us see another example. Say we are taking the statement Pn to be this one: 3 to the power 2n plus 2 minus 8n minus 9 is divisible by 64. So this is a different kind of problem. In the previous one it was a sum of a series that we have to prove. Now here we are having a divisibility type problem. That is, some expression of n is always divisible by a fixed number. So what is the meaning of P1 here? You see, P1 means if you are putting n equals to 1 in this expression and you are getting some multiple of 64 or something which is divisible by 64. So let us see whether P1 is true or not. So for the solution we can write, for n equals to 1, the expression is this: 3 to the power 2 into 1 plus 2 minus 8 into 1 minus 9. And after calculation you are getting it to be 64, which is divisible by 64. Now if it is divisible by 64, then we can say that P1 is true, because whenever you are putting n equals to 1, you are getting the expression to be something which is divisible by 64. So the next step, we will assume that Pm plus 1 we will assume that Pm is true. So assume Pm is true. So then what we can write? We can write 3 to the power 2m plus 2 minus 8m minus 9 is divisible by 64. Now whenever something is divisible by 64, we can write that expression. Here it is 3 to the power 2m plus 2 minus 8m minus 9 to be a multiple of 64 also. See, this expression is divisible by 64. That means whenever we are dividing this by 64, we are getting the zero remainder. That's why we can write this as 64 times k, where k is some integer. Okay, so we will need this equality every time whenever we are proving this divisibility type problem. So this is the thing for Pm. Now we are going to prove Pm plus 1 is true. So for n equals to m plus 1, what we can show, the expression will be of this form: 3 to the power 2m plus 1 plus 2 minus 8m plus 1 minus 9. Since we have to use the mth statement, that is Pm we have to use, that is this equality we have to use, we are keeping 3 to the power 2m plus 2 as it is in the expression of Pm plus 1. So we can write this thing as 3 square into 3 to the power 2m plus 2 minus it is 8m minus it is minus 8 minus 9, that is minus 17. So now see, the value of 3 to the power 2m plus 2 we have to put from this equation. So easily you can see that 3 to the power 2m plus 2 is basically 64k plus 8m plus 9. So if you are putting it here, you are getting 9 64k plus 8m plus 9. Then it is minus 8m minus 17. Now after calculation you can write like this. See, it is a 9 into 8m, that is 72m minus 8, so it is 64m, and it will remain only m in the bracket. And also in the same way, it is 9981 minus 17, that is 1. So this is the thing, it is again a multiple of 64 because the result is becoming 64 times something, so we can easily divide it by 64. So here we can say that Pm plus 1 is also true, so that I am writing here. So hence by principle of mathematical induction we can say, since it is true for P1, since it is true for n equals to 1, and if it is true for n equals to m, it is also implying that it is true for n equals to m plus 1. That means the statement is true for all the natural numbers up to infinity. So this is the way we prove this is the way we solve the problems of this kind. Okay, so here we are finishing this video. In the next video we will discuss some more problems on mathematical inductions. Till then, you try to solve some problems from your exercise book, and we will meet in the next class.